Section: Introduction. In this section, we delve into the fascinating world of large language models, LLMs, and the challenges that come with aligning them to human preferences. It's well known that these models are trained on vast amounts of text, which embeds a myriad of complex preferences and intentions. The big question we, both researchers and practitioners, are trying to answer is how to make these models reflect human values and preferences accurately. One popular method for achieving this alignment is through reinforcement learning from human feedback, RLHF, which adapts techniques from traditional reinforcement learning, like proximal policy optimization, PPO, to maximize rewards based on human feedback. PPO, in particular, has been a go-to method due to its stability and performance. However, it's not without its challenges. For one, it's computationally expensive, requiring several models to be loaded and trained simultaneously. Additionally, the optimization process can be unstable and requires specific expertise to tune effectively. Given these challenges, we explore whether we can maintain performance while avoiding the complexities of PPO. Recent research has proposed various RL-free methods, which simplify the training process by removing reinforcement learning components. However, we choose to stay within the reinforcement learning framework but simplify our approach by going back to basics. We identify key differences between traditional deep reinforcement learning settings, which motivated the use of PPO, and the settings for learning from human preferences in LLMs. Unlike traditional settings, where policies start from a random initialization, LLMs are pre-trained and fine-tuned, which significantly narrows the search space for generating text. This observation leads us to question the necessity of strong regularization and complex algorithms like PPO in this context. Furthermore, we reconsider how learning from human preferences is structured in reinforcement learning. Traditionally, generating each token is seen as an action, and each partial sequence as a state. However, we argue that this is unnecessary for LLMs since human feedback typically applies to the entire generated text, not to individual tokens. This insight allows us to simplify our approach by treating the entire text generation as a single action. With simplicity as our guiding principle, we explore using the reinforce algorithm and its extension, reinforce leave one out, RLOO, to optimize the sequence level objective. Our findings show that the basic policy gradient algorithm, reinforce, consistently outperforms PPO. This suggests that PPO's complexity may not be justified in the context of pre-trained LLMs. Moreover, RLOO, which allows for the use of multiple online samples, not only outperforms PPO but also other baselines, demonstrating its effectiveness and robustness. In summary, our work challenges the prevailing use of PPO for reinforcement learning in LLM preference training. We show that simpler methods like reinforce and RLOO can achieve better performance, reduce complexity, and speed up learning. Our results also highlight the unnecessary complexity of modeling partial sequences and the robustness of RLOO to noise and KL penalty sensitivity. Through our multidimensional analysis, we further showcase the advantages of our approach in terms of language fluency, diversity, and noise robustness. Section Summary. In this section, we delve into the challenges of aligning large language models, LLMs, with human preferences, particularly focusing on the reinforcement learning from human feedback, RLHF, approach using techniques like proximal policy optimization, PPO. We explore the limitations of PPO in practice due to computational costs and optimization challenges, leading us to investigate RL-free methods like DPO and IPO. By emphasizing the use of the reinforce estimator and its extension RLOO, we demonstrate that simpler policy gradient algorithms outperform PPO in LLM preference training, showcasing improved robustness and efficiency in optimizing sequence-level objectives. Section: Background. In this section, we delve into the foundational process initially proposed for refining large language models, LLMs, through a method known as reinforcement learning from human feedback, RLHF. This process is structured into three main stages. Firstly, in the supervised fine-tuning (SFT) stage, we start with a pre-trained language model. This model undergoes further training with a specific set of instructions paired with human written responses. The goal here is to fine-tune the model so that it generates responses closely aligned with the human written examples, using a method called cross-entropy loss that focuses on the accuracy of the generated completions. Typically, the model fine-tuned in this stage serves as a starting point for the next two stages. Next, we move to the reward model stage. In this phase, we employ a reward model that is trained to distinguish between preferred and less preferred completions of a given prompt. This is achieved by training the model on a dataset that includes the prompt, a preferred completion, and a less preferred completion. The training process involves a binary classification task, where the model learns to predict which of the two completions is more likely to be preferred, based on a specific loss function that involves the logistic function. The third stage is the reinforcement learning (RL) stage. Here, the reward model from the previous stage is used to guide the optimization of the policy, the model's strategy for generating responses, in real time. The objective is to maximize a specific function that balances the reward from the reward model against a penalty for deviating too much from the initial policy. This penalty is crucial to maintain the coherence of the model's outputs. Essentially, we aim to optimize the policy in a way that maximizes the expected reward, as defined by the reward model, while keeping the generated responses coherent and aligned with the initial policy. When implementing the RL stage using proximal policy optimization (PPO), we treat the generation of each token as an action and the sequence of generated tokens up to a certain point as the state. The model is rewarded only when it generates the end of sequence token, according to the reward model, with additional considerations for maintaining coherence through a penalty on large deviations from the initial policy. The optimization in PPO involves a clipped objective function that prevents the policy from changing too drastically at each step. In contrast, the reinforce method treats the entire sequence generation as a single action. This approach is more suited for scenarios where the reward is only determined after the full sequence is generated. It allows for direct optimization of the reward objective for the entire sequence, with techniques like subtracting a baseline to reduce variance and improve learning. Throughout these stages, the specific formulations of the reward and the optimization objectives vary, but the overarching goal remains the same: to refine the language model in a way that aligns with human preferences, ensuring that the generated responses are both accurate and coherent. Section Summary. Background. The RLHF pipeline for LLMs involves three stages: SFT stage for instruction tuning, reward model stage for training a binary classifier on preferred completions, and RL stage for policy optimization using the reward model. Different reinforcement learning methods like PPO and reinforce vary in how they formulate rewards, with PPO focusing on token-level rewards and KL penalties, while reinforce treats the entire sequence as a single action for optimization. In this section, we explore how different reinforcement learning techniques, such as PPO and reinforce, adapt reward formulations for optimizing language models in various ways. Section. Reinforce Leave One Out, RLOO. In this section, we introduce the concept of reinforce leave one out, RLOO. The basic idea we start with is quite straightforward and doesn't require much computational effort. However, we found a way to enhance it when we have multiple online samples at our disposal. These samples can be used in two key ways to further reduce bias without adding extra variance. First, by using the rewards from each sample as a baseline for all the others, and second, by averaging the gradient estimates from each sample for policy updates. This approach leads to a more refined estimate that's less scattered, which is the core idea behind the RLOO estimator. In more detail, when we have a number of online samples, we treat each one individually but use the rest to create an unbiased estimate of the expected return. This method acts like a dynamic, parameter-free value function that's recalculated at every training step, making it a more effective baseline than traditional methods. However, it does require more time to sample during training. Moving on to alternatives to reinforcement learning in preference training, we note that there's a significant body of work proposing methods that don't involve the third stage of reinforcement learning. We compare reinforcement learning approaches like PPO, Reinforce, and RLOO against these alternatives, including Direct Preference Optimization, DPO, and RAFT. Specifically, iterative fine-tuning methods use the trained reward model to rank different outcomes and then iteratively fine-tune the policy based on a selected subset. This approach, which combines rewards from reinforcement or bandit learning with supervised learning objectives, has shown success in offline reinforcement learning for natural language processing problems with large action spaces before the advent of reinforcement learning with large language models. RAFT, for instance, uses a simple cross-entropy loss on the highest-ranked completion out of several online samples, based on their rewards. However, RAFT doesn't utilize all samples fully since it only optimizes using the top-ranked samples. In contrast, RLOO takes full advantage of all samples by constructing a baseline and a multi-sample Monte Carlo estimate for the policy gradient. We also examine the components of PPO and question their suitability for reinforcement learning with human feedback, RLHF. PPO was designed to address the high variance seen in traditional reinforcement learning settings by using lower variance estimators. These estimators bootstrap off a state value function to improve learning. While this does reduce variance, it introduces bias, which can lead to optimizing for biased rewards. Reinforce, on the other hand, uses an unbiased Monte Carlo estimator that, despite potentially having high variance, doesn't introduce bias. Recent studies have shown that Reinforce struggles with large action spaces, such as those in natural language processing. However, these studies were based on scenarios with poor initial conditions, unlike the strong starting point provided by a pre-trained large language model. In such a scenario, the strong initialization and prompt conditioning concentrate the probability mass on a few tokens at each generation step, reducing the likelihood of encountering problems like large, high-variance gradient updates. Therefore, we argue that further reducing variance at the expense of introducing bias is unnecessary in the context of fine-tuning large language models. To support our hypothesis, we experimented with varying the emphasis on minimizing variance versus introducing bias. Specifically, we looked at the Generalized Advantage Estimation, GAI, in PPO, which uses a hyperparameter to balance bias and variance. Our findings suggest that in a stable environment like RLHF, where variance is already low, introducing bias is unnecessary. Our results show that the variant of the policy gradient that introduces the least bias, even at the risk of higher variance, performs the best, supporting our hypothesis that in RLHF, reducing variance at the cost of bias is unwarranted. Section Summary. In this section, we introduce the Reinforce Leave One Out, RLOO, estimator, which leverages multiple online samples to create a variance-reduced multi-sample Monte Carlo estimate for policy updates. RLOO constructs an unbiased estimate of the expected return for each sample individually, enhancing the baseline compared to traditional methods like PPO. By balancing bias and variance, RLOO proves to be a more effective approach for RL in high-fidelity fine-tuning, RLHF, tasks, especially when fine-tuning large language models, LLMs, due to their strong initialization and prompt conditioning. Section. Clipping is rarely necessary in RLHF. In this section, we discuss how clipping is not often needed in reinforcement learning with human feedback, RLHF. We explore the concept of a clipping ratio, which is designed to prevent significant policy updates if the ratio of the new policy to the old policy strays too far from 1. This means it's there to stop changes that could drastically move away from the current policy. Through our experiments, which involved comparing reward curves from training with and without clipping, we found something interesting. We also chose to disable clipping for the value network in these experiments, as its impact on learning has been noted in traditional deep reinforcement learning environments. However, removing these components didn't significantly affect the learning process. Our findings in the RLHF setting revealed that the loss was clipped less than 5% of the time per batch during training, across all datasets and model pairings. This suggests that the learning process is mostly on policy, with policies changing gradually from one iteration to the next. To dive deeper, we completely turned off clipping and removed the policy ratio while setting lambda to 1, simplifying the proximal policy optimization (PPO) loss to that of vanilla policy gradient (PG). Interestingly, removing clipping seemed to slightly improve performance, supporting our belief that large off-policy updates are uncommon in our optimization regime and do not negatively impact learning as they might in traditional deep reinforcement learning. Moving on to the topic of modeling partial completions, we explain that in the context of RLHF for large language models, LLMs, it's not necessary to model each token as an action. Instead, a reward is only given to the end of sentence EOS token, making the reward for other tokens not meaningful. From a pure reinforcement learning perspective, the environment dynamics are fully deterministic, meaning the environment changes predictably with each new token or action. This simplifies the problem to a bandit problem, where the Markov decision process, MDP, only involves the initial state set by the prompt and the terminal state reached after generation. This approach, modeling the entire generation as a single action, is not only explicit in reinforce but also implicit in iterative fine-tuning methods that generate the entire completion before filtering with a reward model. In the results section, we will compare reinforce and RLOO, which model the full trajectory return, to PPO and vanilla PG, which model the partial completion, to see if modeling the entire generation as a single action is sufficient for achieving similar or better performance in RLHF. In terms of our experimental setup, we report results on the TLDR summarize and Anthropic helpful and harmless dialogue datasets. The TLDR dataset includes human written instructions and human annotated preference pairs, while the preprocessed Anthropic dataset contains many training preference pairs. We use the PyTHIA 6.9b model for both datasets and also test the Llama 7b model with the Anthropic dataset to see how pre-trained model quality affects optimization of human preferences. We maintain a consistent context length of 512 tokens for both supervised fine-tuning and reward model training, starting both the reward model and policy from the same supervised fine-tuning checkpoint. For evaluation, we measure optimization quality by reporting average rewards on samples from the test set and simulated win rates to assess alignment with human preferences. We use greedy sampling for evaluation unless stated otherwise. We also address the alignment tax, which refers to the potential drop in diversity and language fluency during RLHF fine-tuning, by reporting metrics that serve as proxies for fluency and diversity, including perplexity and average n-gram diversity, measured using preferred completions from the test set. Section Summary. In this section, we discuss the rarity of clipping in RLHF. We explore the impact of the clipping ratio epsilon on preventing large policy updates and note that in our RLHF setting, clipping is only applied around 5% of the time per batch, indicating a close to on-policy learning regime. Additionally, we find that modeling partial completions is unnecessary in RLHF, as the environment dynamics are deterministic, reducing the problem to a bandit problem where the entire generation does not need to be modeled as a single action. Section: Reward Optimization. In this section, we discuss how our goal across various methods like RLOO, reinforce with a moving average baseline, RAFT, PPO, and the basic policy gradient, PG, approach is to maximize the reward score. We ensure a fair comparison by using the same reward model across all methods, allowing us to directly compare their success in optimizing rewards. We observed that methods which do not account for partial completions, such as reinforce with a baseline and RLOO, consistently perform better than vanilla PG and PPO, which treat each token as an individual action. This advantage is not just in reward optimization but also in efficiency, as they require one less model copy and do not need a learned baseline or a value network, unlike vanilla PG and PPO. When it comes to using our resources wisely, RLOO stands out. Given the same number of online samples for each prompt, RLOO consistently outperforms RAFT during training. Interestingly, even with half the sampling budget, RLOO matches or even exceeds RAFT's performance across various datasets and models. This efficiency is highlighted by RLOO's ability to utilize all generated samples effectively, unlike RAFT, which only uses the top-ranked sample for fine-tuning. In terms of simulated win rates against original completions, our findings show that not modeling partial completions does not hinder performance. Reinforce with a baseline competes closely with vanilla PG and even surpasses it in certain datasets, emphasizing the effectiveness of treating the entire generation as a single action. RLOO, especially with a sampling budget of 4, achieves the highest win rates, significantly outperforming PPO. This trend is consistent across different datasets, showcasing RLOO's superior sample efficiency compared to RAFT. We also explored various intrinsic evaluation metrics like perplexity and diversity scores. The DPO-trained model tends to produce longer responses, while the PPO-trained model generates shorter ones. Despite these differences, RLOO, RAFT, and Reinforce with a baseline achieve lower perplexity scores than PPO and vanilla PG, indicating better fluency. However, as reward optimization increases, we noticed a slight decrease in diversity scores, which is expected given the variation in generation lengths. Lastly, we aim for lower reward variance in applications where generating a low reward sample poses a high risk. RLOO demonstrates slightly lower reward variance compared to RAFT, making it a more reliable choice. Reinforce with a baseline, in particular, shows 27% less variance than vanilla PG, further proving its efficiency in both reward optimization and maintaining consistent win rates. In summary, our analysis highlights the benefits of not modeling partial completions and the efficiency of RLOO in using resources wisely, leading to better reward optimization and reliability in generating high-quality responses. Section Summary. In this section, we compare various reward optimization methods such as RLOO, Reinforce with a baseline, RAFT, PPO, and vanilla PG to maximize reward scores. We find that methods like Reinforce with baseline and RLOO, which do not model partial completions, consistently outperform vanilla PG and PPO. Additionally, RLOO demonstrates better sampling efficiency compared to RAFT by using all generated samples for optimization, leading to lower reward variance and higher win rates across different datasets and models. Section: Robustness. In this section, we discuss the robustness of our approach. We've noticed a significant limitation with the RAFT method, which is its focus on optimizing only the top-ranked sample while ignoring the rest. This means that any factors causing an incorrect ranking of the best completion can greatly hinder the learning process. To illustrate this vulnerability, we compare the effects of two specific conditions on RAFT and our method: RLOO, a high value for the KL terms beta, and the introduction of reward noise. Firstly, we explore the impact of mismatch from the KL penalty. Through our experiments, which involved using a set of models based on Pythia on the HH dataset with 2 online samples, k equals 2, we varied the KL regularization by setting beta to 0.25, 0.5, and 1. This showed us that a larger KL penalty, indicated by a higher beta, could lead to a greater mismatch in the ranking of the online samples. However, the choice of beta is influenced by several factors, such as the data distribution and the output logits from the base model, which might not always allow for a lower beta value, even with the implementation of early stopping. Our findings reveal that RAFT is particularly sensitive to higher levels of KL regularization. In scenarios with low regularization, beta equals 0.1, both RLOO and RAFT eventually matched in terms of KL distance from the reference policy, but RLOO achieved a higher reward. With increased regularization, beta equals 0.25, 0.5, 1.0, not only did RAFT perform worse in optimizing the reward, but it also deviated more from the reference policy. Secondly, we address the mismatch from reward noise. Given that the reward model is a noisy approximation of the actual reward signal, we drew inspiration from Bayesian deep learning literature on modeling uncertainty to simulate the effect of varying degrees of noise. Specifically, for each prompt, we added noise to the output logits of the binary classifier, where the noise epsilon follows a normal distribution with a mean of 0 and a variance of sigma squared. Our results, which looked at noise levels sigma equals 1.0, 3.0, and 5.0, showed a decrease in training reward for both RLOO and RAFT. However, RAFT experienced a significantly larger drop in reward at the higher noise levels, sigma equals 3.0 and 5.0, due to the added reward noise affecting the relative rankings and, consequently, the training reward. In contrast, RLOO demonstrated a more robust optimization of reward under noisy conditions. In summary, our analysis highlights the fragility of RAFT when faced with high KL regularization and reward noise, and showcases the relative robustness of RLOO under these conditions.